Alright, so everyone, today we are talking about the Force. No, not this kind of force, even though we'd like to, but not today. No, today we're talking more like forces that kind of push blocks over on tables, things that you kind of see every single day, the things that make our general world go around. We're going to start off with that you guys should have opened the Forces graphic organizer from Google Classroom. If you haven't done that yet, please do so now. This is the first slide. It should look like this. We're going to kind of step through it together. So these first two questions here are really just more of a review of what we talked about the last couple days. Take a minute, pause the video, respond to these two questions, and then we'll kind of be applying this to what we're going to see here in the coming days. So we're going to start this off with a short definition, I think, one that you guys already all know, and that is, what is a force? Well, a force occurs anytime that you push or pull on something. As a matter of fact, I would argue that if you break it down to the basics, a push and a pull is basically the same thing. So that's what we're going to start off with. Get this definition down in the beginning. A force is a push or a pull on an object. Now, it's very important to note that every force has two basic parts that describe it. You'll see the 1 and the 2 at the top. Starting off, every force has the strength. How strong is it? Is it a big force? Is it a little force? So for number 1, we guys are going to put size. All right, the size of the force. Then number 2, also hugely important, is going to be the direction. What direction is this force going in? Are you pulling something up? Are you pushing something down? Pulling it to the left? Pushing it to the right? The direction is going to be hugely important. So anytime you talk about a force, anytime anyone talks about a force, they have to not only say how big of a force it is, they also have to discuss the direction in which the force is going. And it's this reason that we identify force as a vector. Again, all vectors have both size and direction. Here we talk about the strength and the direction. So for 1 and 2, you should guys make sure you get down size and direction or strength and direction. What we're going to see a lot of is drawing forces acting on objects. And the easiest way to draw a force, the most clear way, is using an arrow. Now, obviously, a couple basics on how this is going to work. First, I think we get to the most obvious bits, and that is when you're dealing with arrows, well, how do you discuss the size and the direction? Well, of course, the tip tells you what direction the arrow is pointing in, so that direction the force is going in. And then, to be clear, for the size of the force, we change the length of the arrow, not the width of it. So you'll see longer arrows for stronger forces and shorter arrows for weaker forces. So here we would see a large force pushing this box to the right. Pretty straightforward. In this example, we see a smaller force pushing the box to the right. Again, because it has the shorter length. Here now we see the force pushing the box to the left. Again, it's a larger force due to the longer arrow length. I don't think we're breaking any new ground here for most people, but I would like you guys at the bottom of the screen here to go ahead and put some arrows on those boxes being pushed by the hand to indicate both the size and the direction of the arrows. Take a minute and do that, please. The last thing to cover on this slide is going to be the unit that we use to measure. The unit you've used for force in the past is likely the pound, and that is the imperial unit used by those descendants of the British Empire. Basically, what we're looking at now in science is that nobody uses pounds for the unit for force. Instead, we use the standard metric unit of newtons, named after Sir Isaac Newton. To give you an idea, so most of you know what 1 pound is. Well, what's 1 newton? 1 newton is roughly the weight of a medium-sized apple. So then if you were to do something like have a sack of apples and you wanted to report the weight, the force of the apples, you would say something like 10 newtons down, and it would be written like this. So that's all when you're dealing with one individual force. But what happens when you have a bunch of forces acting on one object? So here you see a bunch of people pushing on a car, trying to push it in the dirt or the mud, whatever. So now you have multiple forces acting on one object. How do we take care of that? That's when net force comes into play. So in math class, they say net pretty much means the sum of things. So when you add them and subtract them together. A lot of people just say, oh, net force is when you add the forces up. But you have to realize that forces have direction, and directions essentially lead to them having signs in math. So you can't just always add all the forces together. So basically here I have two 10 Newton forces pushing to the left on this box. So I would sum these together, and would you say 20 newtons? If you did, you'd be wrong. This would be 20 newtons to the left. You have to give that direction. It's going to be really important. So in this next example here, we'll see that you have 10 newtons pushing to the left and 10 newtons pushing from the right. When you sum these together, should we add them like we did before? No, now they're going in opposite directions. When they're in opposite directions, you would subtract them. So 10 minus 10, of course, would give us a 0 newtons. Now here's a stickler on a point that I made before. Because the net force is 0 newtons, you don't have a direction, much like 0 does not have a sign in math. 0 is neither positive nor is it negative. Here, it's neither to the left nor to the right. The last one here I would like you guys to do on your own. Come up with your answer, put it on your graphic organizer with the others, and then we can talk about them later if you have questions. Don't forget your unit, and don't forget your direction. So when your net force adds up to something other than 0 newtons, then you're left with what's called an unbalanced force. That is, you have more force pushing in one direction than the other directions of an object. This is going to cause one of three things to happen. And whether you are the driver or not, you have experienced all three of these things in a car. The first possibility of an unbalanced force is that you cause your object to speed up, going faster and faster and faster, such as this rocket car here. The second possibility being that you slow down, coming to an abrupt stop, perhaps in a crash, perhaps not, but either way, the result of an unbalanced force could slow an object's motion. The third possibility of an unbalanced force is neither speeding up nor slowing down, but instead here changing direction. It is possible to make a bend, to make a turn without speeding up or slowing down, and then you have to apply a force to the object to actually do this, an unbalanced force that is. You've kind of experienced this unbalanced force act on you before when you turn, especially you'll see motorcyclists, when they turn, they have to lean into that force, otherwise that unbalanced force kind of throws them off their bikes. So three possibilities that we have. When you're looking at the unbalanced force, that is a net force, again, of something not equal to 0, you could be speeding up, slowing down, or changing direction. This may or may not sound familiar to you, but these are also the three ways that an object can accelerate. Acceleration is defined as the change in an object's velocity, so basically that is causing it to speed up or slow down, so changing its speed, or thirdly, changing its direction. So what I want you guys to pull away is that unbalanced forces cause acceleration. When the net forces on an object are balanced, that means the net force is 0 newtons, then you have a much different scenario. Basically what's happening here with no net force, you are not having anything change the motion of the object, so the motion should remain constant. If you just kind of look around your room and find some object that's just sitting there on your table or whatever, say, hey, yeah, gravity's pulling it down, the table's pushing it back up, these forces are equal and opposite, the motion doesn't change. Now, if you go over there and push it and change the forces so then you have an unbalanced force, then yeah, you can knock it over, but as long as those forces remain balanced, then the object's motion should not change. A point that many kids confuse here is they think that if the forces are balanced and there's no net force, then the object must be sitting at rest, that it's not moving. That is not true at all. To give an example of this, consider the Voyager probe. The Voyager probe was shot out into space back in the 60s with the intention of taking pictures and gathering information of our own solar system, but then eventually to travel outside of our solar system and with the potential of one day coming in contact with some other intelligent species in space and communicating information with them. Basically, the idea was that we aimed it really well to make sure it wouldn't crash into anything, and we shot it out into space, and once it left, once it passed all the major objects in our solar system, there are now no net forces acting on this probe, and it continues to be in motion, just traveling through space, on and on and on. Just recently, it passed the Oort cloud, which is a cloud of meteors and I say asteroids that are out beyond Pluto. So it is the first man-made object to have ever left our solar system. And now that it's all out of our solar system, it will continue going and going and going, just drifting on, because the forces acting on it are balanced. For this final slide here, what we'd like you to do is just take a chance at identifying the different forces acting on these objects. So in the example on the left, you see Isaac Newton with an apple falling down. You see the arrows acting. There are two forces acting on that apple. What two forces do you believe that they are, and are those balanced or unbalanced? Likewise, if you look at the, that's not luging, what is that? Bobsledders. If you look at the bobsled, you have one person pushing to the right, and then you have something else going to the left. Identify what those forces are, and are they balanced or unbalanced? That's what we have for today. You guys have a great one.